Hello, chemistry students. Today is the last lesson of Unit 1, Chemistry of the Big Bang, and today's lesson is on half-life. If we look back at the objectives from Lesson 12, it had the half-life objectives on there. We are today going to determine the half-life of a radioactive element and also use the half-life to determine how much of a isotope may still be remaining. And then also, the latter part of this lesson is to talk about differences between different types of transmutations, whether they be natural or artificial. So, what is half-life? Well, if you look at this graph, this shows how radium would decay over time. So if we had 1 kilogram of radium in the beginning, after 1,620 years, the half-life of radium, we would have half a kilogram. Notice the half-life is the amount of time it took for half of it to go away. But here's where it gets interesting. If we go another 1,620 years, so now we have 2 half-lives. We have cut the original in half and then cut this half into half, leaving a quarter. Then another 1,620 years goes by, and that quarter gets broken down by another half and becomes an eighth. And essentially, this material would never go away until you're down to the last atoms. So half-life is the amount of time it's required for half of the sample to decay. Say that again. It's the amount of time, the life, half-life, the amount of time that it requires for half of the sample to go away. And in what's called a first-order decomposition, every half-life, another half of the material is gone. Let's look at another example. Suppose we started off with 1,000 nuclei, and we know that the half-life of this particular nuclei is 5 years. This is just to make the numbers easier. So after 5 years, I'm going to have how many? Well, 5 years is my half-life, so I'm going to have, let's see, half of that would be 500. Okay. Then, what about in 10 years? Well, that's 2 half-lives. So if I had 500 after 5 years, I would have 250 after 10 years. 2 half-lives are going by. I've cut it in half twice. Trying to get out my pen, sorry. I'm down here. So after 5 years, I had 500. After 10 years, I'd cut that down to half again, and I'd have 250. Let's see. What about in 15 years? Well, another half of life has gone by, so I'd have half of that, which would be 125. And then what about 30 years? Oh, that's going to be interesting. So if at 15, I have 125, okay, that means at 20, I would have 62.5. Is that right? 1, 2, 2, 5. I think so. And then after 25, I would half of that would be 31 and 2.5. And then after 30, at half of that, let's see, that would be 15.625. I think that's right. So every time 5 years goes by, cut it in half, cut it in half, cut it in half, until you get down to your expected amount of material. Okay, so I'm going to put this video in Schoology. If you look at it, is talking about its half-life and talks about how the carbon-14 is used to determine the half-life, determine the age of various living or formerly living materials. So let's talk about what happens. So when talking about organic matter, for instance, in 1991, there was a discovery of something called the Iceman because he was found in ice completely encased. You can see, look at the guy. He's not in really great shape. been dead for a bit. They looked at the Iceman's chemical makeup, and they noticed that the amount of carbon-14 that is inside of the Iceman at that time was about half what it would be if he were alive today, meaning that the Iceman, in the time that he has been expired, was perpetually decomposing carbon-14 into nitrogen-14. And in that process of going from carbon-14 to nitrogen-14, he was decaying. But since the Iceman was no longer eating carbon-14 from the surroundings, all the carbon-14 got broken down. Well, what does that mean? If he has half of what he should have, that means it's been one half-life of carbon-14, and so be it that half-life of carbon-14 is 5,700 years, give or take. So that means that Iceman's body had died, stopped living, became unalive 5,700 years ago, give or take. So this is the way that carbon dating is done. You take a living material, which is in a living situation, would be constantly absorbing carbon-14 from the surroundings as it expels whatever material it has, and is constantly keeping its body, keeping the living material at a constant level for carbon-14. But as soon as that thing expires, dies, becomes unalive, it no longer brings in carbon-14, but the carbon-14 in its body starts to decompose or decay. So you can measure the amount of carbon-14 relative to what it should be, and that can give you a really good idea of how old or how long this thing, this person, this Iceman has been dead. Kind of interesting. Now, it doesn't work on rocks. Why is that? Because rocks don't bring in carbon-14. They aren't living. They're constantly doing that. They got to use other things on rocks. Okay, let's talk about all this, wrap this all up with a big bow, talking about transmutations. So transmutations are all the situations we talked about for the last 3 lessons about how nucleus can sometimes transform into another element. That's unusual. This whole 3 lessons on radioactivity and radiation revolve around the fact that you're going to have elements that are going to change identity. They're going to change identity because they're going to change the number of protons in their nucleus. If an element undergoes a transmutation and it releases energy, then that's considered to be radioactive. It releases energy during that change. Now, there are different types of transmutations. There are the artificial ones and the natural ones. In an artificial one, you have the change in the nucleus that happens, but it normally happens as you initiate or bother the nucleus. Do you remember back when we were talking about nuclear power plants, they had to be initiated by hitting the nucleus with neutrons? Well, that would be an artificial transmutation. That element was okay, it was fairly stable until it was bombarded with neutrons, and then the new extra neutron element is unstable and it breaks down into its parts. So you're going to have some other sort of reactant there besides the original particle. So for instance, if I shoot an alpha particle at nitrogen-14, it is going to become oxygen-17 and it's going to kick out a proton. That is essentially having the 4-2 come in and change over and change the makeup of the nitrogen to make it oxygen. Another one would be calcium. Calcium-44, when it's hit with a neutron, that calcium-44 is going to become calcium-45. It's just going to add a neutron directly to the atom. It's not going to change the identity, but it's going to change the nucleus. That has to happen as we add a neutron. What about the natural ones? Well, those are the ones that happen spontaneous. It's an atom that is naturally going to decompose, one of the examples would be carbon-14. Carbon-14 spontaneously decays into nitrogen-14. It's going to happen spontaneous. It doesn't require any other reactant. The only reactant is the atom that's going to undergo that transmutation. So an example might be uranium-238, becoming naturally, because uranium-238 is unstable, naturally becoming thorium-234 and releasing an alpha particle. That would be an example of a natural transmutation. So the difference, natural, it is an unstable nucleus that breaks down, changes because it needs to become more stable, versus artificial, it's on the fringe of being unstable, but when it's initiated with adding a alpha particle or adding a neutron, the nucleus becomes even more unstable and then will break down into some other atom. So that's it for chapter Unit 1 and lesson number 13. Hopefully this has been some help, and hopefully you've been staying on top of the notes and staying on top of the homework. Unit test coming up in a few days. So until then, toodles. I'll see you in class.